Welcome back to our final units in IB math class. So we are going to talk on this Wednesday, or whatever day you're doing this assignment, about adjacency matrices, not adjacency tables, and transition matrices. So what we're going to be doing is turning our information into matrices. All right, so first, adjacency matrices. Sorry, you know I have issues with this smartboard. Hello. All right, so here, I'm sure you can read that up top, but I'm going to read it out loud. Two vertices are said to be adjacent if they are directly connected by an edge. That is the definition of adjacency. An element, A sub ij, of an adjacency matrix A is the number of direct connections between vertex I and vertex j. Right, and so this I and j is basically going to be defined by the points, the places. So let's find the adjacency matrices for these two graphs. Let me start with graph A. All right, and so first of all, we want to figure out how many vertices are on this graph, A, B, C, and D. There's 4 vertices. So we are going to label our matrices as such. A, B, C, and D across the top, A, B, C, and D for the rows as well. All right, and let's fill in our values. Now we can see here this is an unweighted graph, all right, and there's also no direction. Okay, so from A to A, well, nothing really there. From between A and B, there is one direct connection, and so from A to B, also right here, there's a direct connection. From A and C, yep, there is a direct connection. A to C, again right here. From A to D, no direct connection. And right here, again, a 0. All right, from B to B, there's no edge, no connection really there. From B to C, we do have one. We're going to put a 1 here. And from, B to C, put a 1 here. And from B to D, there is nothing. All right, and so from D to B, yep, there we go. Lastly, from C to A, we have a connection. C to C, no connection. I mean, it's C. C to D, we have a connection. So this one right here, and this one right here, and then D to D, no connection. So this is our adjacency matrix for this unweighted graph in the bottom left. All right, and so this is an unweighted graph as well as an undirected graph. And so you're going to notice this is a difference between this matrix and the next one we're going to do. So since this is undirected, you'll see zeros on this main diagonal. Now, let's work on this directed graph, which is B. All right. All right, so again, A, B, C, and D. Look at this. This is the same. It's almost the same graph, but we see it's directed. Sorry, I kept saying weighted before. I meant directed. All right, so again, vertices A, B, C, and D. C, D, A, B, C, D. And just like our example in class today, since this is a directed graph, we're going to go from row to column. All right, so let's take a look here. Can we go from A to B? Yes. So from A to B, yes. All right, A to A, we're going to call that a no. Can we go from B to A? B to A? No. All right, can we go from C to A? Yes. All right, and can we go from D to A directly? No. All right, now you can do these in any order that you want. I'm just going to continue like this. All right, so from A to B, we said yes. How about from B to B? We'll call that no. From C to B, yes, we can. From C to B, yes, we can. And from D to B, nope. All right, from A to C, yes, we can. From B to C, nope. C to C, nope. D to C, yes. Lastly, from A to D, nope. B to D, nope. C to D, nope. D to D, nope. Wait, where did we go? Oh, D is only from. Okay. All right, so we do have zeros in the main diagonal here. Gosh, sorry. Again, zeros in the main diagonal. What's different about this one, though, is that there's no symmetry about that diagonal. Oh. All right, because this is showing the directions. This one right here shows directions, so this is directed. And so there's only certain cases where you can go to and from between the same vertices. Whereas in graph A, since it is undirected, we're just showing the connection. So we can see this symmetry. Boop, 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 across that main diagonal. All right. Okay, so for this one, I will ask you to pause the video here, try it out yourself. I'm going to put up the answer key in a moment, and when you replay it, you will see the answer key for part A, and then we'll do the same for part B. Okay, so let's check our answers here. For part A, hey. So for part A, you'll notice some different numbers that we didn't see in our previous adjacency matrices. You're going to notice this, sorry, I'm trying to get this color on the board. This 2. This represents, remember, the adjacency matrix shows how many direct connections between those two vertices there are. Notice there are 1, 2 direct connections between A and C. So that's why this 2 is in these 2 parts. And remember, this 2 is symmetrical about that main diagonal because this is an undirected graph. Another thing you'll notice that's interesting is this 1 right here, where we have from D going to D. That's because of this right here. Okay, it's not just a point, an edge rather. It's not just a vertex. It is showing a loop there, so we can get from D to D. Now pause and let's turn this into a directed, an adjacency matrix for a directed graph. Pause, and then I'll show you the answer key that I've got in a second. All right, so here's the answer key for question B. The directed graph, same vertices again, and we'll notice since this is a directed graph, we're going to read it as from A to A, right? From A to B, from A to C, so on and so forth. Now we'll notice here, this 2 means that from C to A, there are 2 ways of getting there, all right? Those are those 2 arrows, but from A to C, this 1 is showing us this guy with that arrow. And again, this loop-de-loop here is indicated by this 1 from D to D. All right, so next up is this problem from exercise 15C. And we can walk through this one together. What is this? 15C. Okay. So this adjacency matrix is showing relationships between people, all right? And so this is a directed graph. It says where a 1 in the entry in row I and column J indicates that person I knows the name of person J, all right? So rows are I, columns are J. So what this means here, for example, this one, it means A knows B, knows B's name, rather. All right, so let's go through these questions. Question A1, explain why the matrix has a 1 in each entry on the leading diagonal. Because everyone knows their own name, I'm guessing. All right, so A knows his or her own name, B knows their name, C, D, and E. All right, explain why the graph does not have to be symmetric. Now, remember we talked about this in the other 2 problems. The graph will be symmetric along that diagonal if it is undirected. This is a directed graph. It's saying who knows whose name. In other words, in which direction this sort of relationship goes. Now, without drawing the graph, we can get a lot of information from this matrix. How many names does person A know? Okay, so this column is telling us how many names person A knows. All right, and so then that is 1, 2, 3. Person A knows their own name, knows B's name, and knows E's name. The number of people who know the name of C. So now this right here is saying how many names C knows, but this right here is telling us how many people know C's name. Again, 3. who knows the most names? All right, well, the people knowing the names, those are the rows. And so we look for the most ones there. Sure looks like C knows the most names. And whose name is known by the largest number of people in the group. That's similar to problem 2. So where do we see the most ones in the columns? Who is most popular, it seems, is E. That is E. All right. Is there anyone who does not know A's name and also does not know anyone who knows A's name? Okay, well, the people who don't know A's name, let me just erase this, are, look for the zeros in the column A. All right, so these people don't know A's name. Okay, now between C, D, and E, do C, D, and E also not know each other? Well, not know each other's names. C knows D and E's name. D knows C, D, and E's name. E, however, does not know C's name. And so E is that one person who is a little lost. All right. So next up, I'll put on a new screencast, is going to be, oh no, actually I think I can do the other part of this in this screencast. Okay, let's see another way that we can use an adjacency matrix. This information in the top right corner is telling us that the number of walks of a certain length between two different vertices on a graph can be found by finding the corresponding entry in the matrix raised to that power. All right, and if we need to find the number of walks of up to a certain amount, well, we're going to sum some matrices of certain powers. So let's take a look at exercise 15D. This is going to show us one of these problems. Now, this is referring actually to the problems from exercise 15C. So I'm just going to work with, what is this, A, B, C, D. I'm just going to work with this, here we go, this adjacency matrix, which corresponds with this graph. All right, and we're going to answer these questions. Use these matrices, well, use this matrix to find the number of walks of length 3, exactly 3, not up to 3 or 3 or less, but exactly 3. All right, between A and A. Okay, so that means I'm going to just call this M. All right, and so we're going to take this M and raise it to the third power. Okay, and so I'm going to write that over here, A1. M to the third power is going to equal, and I just put that in my calculator. It gives us 2525, 5455. Notice A is an undirected graph. 2525, symmetry again. 5554. Okay, so then between A and A, how many walks or routes in regular people's terms are there between A and A? 2. All right, and so our answer here is 2. And let's verify this. All right, so between A and A, walks of length 3. Okay, so we could go 1, 2, 3, A, B, D. Let's verify this. From A to B to D. We could also go from A to D to B. 1, 2, 3. A to D to D to B. And 1, 2. That's it. There's no other way of getting from A to itself in 3 walks or less. All right, so A, B, D. Oh, sorry, I didn't include the last letter. A, B, D, A. A, D, B, A. Okay, now this same matrix we can use for the second question to get between C and D. So this is an undirected graph again. And so let's use that same matrix because we're looking for how many walks are there of a length exactly 3 between C and D. And we'll notice that the numbers in the corresponding entries are the same because this is undirected. All right, so between C and D, let me just jot this down. A, B, C, and D. A, B, C, and D. Okay, so between C and D, 5 here and a 5 here. Our answer is 5.